Hello everyone, welcome back to the channel. For today's session, we're going to look at a Lagrange equation. You can find more info in your lecture notes in page 47. So what is Lagrange equation? Alright, Lagrange equation is an approach that can be used to construct equation of motion. And using this approach, you don't need to draw free body diagram like in Newton's second law, whereby in Newton's second law, if you want to construct the equation of motion, generally you need to draw the free body diagram, and then from the free body diagram you can get the equation of motion. But for Lagrange, basically you only need to refer on this. Okay, this is the equation for Lagrange that can be used to construct the equation of motion, whereby you can also find this in your page 47 lecture notes. Okay, so if you look in here, in the box here, the equation, alright, so the differentiation of dt over dq dot j, q dot here, minus dt over dqj plus dv over dqj equals to qj. So what is in here? T is the total kinetic energy, V is the total potential energy, Qj is generalized coordinate, and capital Qj is non-conservative generalized force. So if you look here one by one, for T, total kinetic energy, okay, for total kinetic energy, we've got two cases. One, if we have translational vibration. For translational vibration, the total kinetic energy would be half m v squared, or in vibration we write it as half m x dot squared. Alright, this is for translational vibration, where you have spring and mass system. How about for torsional vibration? For torsional vibration, the total kinetic energy would be half j theta dot squared. Okay, this is the case for rotational or translational vibration. So for the total potential energy, you can also describe it in two cases, whereby the potential energy, maybe I'll change it to rate. For total potential energy, and for translational vibration, we could write it as half k delta x squared. So this is the case for translational vibration. And for rotational vibration, it will be half kt, which is this torsional stiffness, delta theta squared. This is for torsional. So far it's very simple, right? Okay, and then what is qj, the generalized coordinate here? We can also describe in two ways, which is for translational vibration, q is equals to x. Okay, this is for translational. And for rotational vibration, q is theta. Okay, I assume all of you should know this by now. Okay, this is the coordinate used for a vibration. And what is Qj? Qj is non-conservative generalized force, where we could also describe in two cases, whereby for spring mass system, translational, Qj is equals to F. This is for translational. And for rotational vibration, Qj is actually your moment. Okay? So generally, if you could find all of these, okay, you can use this equation in order to get the equation of motion. Alright, let's look on a few cases here in order to aid your understanding. So let's say we assume a case of 1 degree of freedom. Okay, this is a translational vibration where we have a spring mass system. This is how I always do it. First, when I'll get the problems, and identify the generalized coordinate first, whereby in here the q, because it's a translational system, therefore q is x, okay, which is this, q equals to x. And then next I identify the total potential energy. So because we only have one mass here, therefore the total potential energy is half m x dot squared. Okay, and we know that we're going to use this equation in order to get the equation of motion. So I need to identify dt over dqj, anything related to t. Same goes to this one and also this one. Okay, so I'm going to write it later. So from t is equal to mx dot squared, therefore dt over dqj, dq dot j is also be written as dt over dx dot, which is mx dot. Okay, if we differentiate dt over dx dot, if we differentiate this, we will get mx dot, and d over dt, dt over dx dot is equals to mx double dot. Okay, so if we differentiate this towards time, we will get mx double dot. Okay, so why do I find all of this? Because in here, if you refer to the Lagrange equation, generally we need to find this, and we also need to find this, which is related to the potential energy. So for dt over dqj, which is actually dt over dx, because our generalized coordinate here is x, and if we refer here, we don't have any terms of x, we only have terms of x dot. Therefore dt over dx is 0. So we've got this one and also this one. Now we need to identify dv over dqj. First, we need to write the potential, the total potential energy, whereby V is half k delta x squared. Okay, delta x is actually the difference between x initial, and in here, because we only have one x here, we don't have x1, we don't have x2, we only have one x here, therefore the equation can be written as half k x squared. So this is the total potential energy, and so from here, dv over dqj, as stated in the Lagrange equation, is actually dv over dx. So if we differentiate this towards x, we will get kx. Right, so we've done this part. I've got this right now. And then the last thing is the force, qjn. So if you look in the problem here of the system, we don't have any external force. Therefore, qj, or in this problem is qx, is equals to 0, because it's a free vibration, it doesn't have any external force. Therefore, by using the Lagrange equation of, I write it back in order for you to easily understand. So d over dt over dq dot j minus dt over dqj plus dv over dqj equals to qjn. Okay, so from all of the info that we got, therefore this one would be this one. Okay, d over dt dq dot j is this one. dt over dqj is this one. dv over dqj is this one. Maybe I should change color in order for you to see it easily. So generally it's this one, and this one. Therefore, the equation of motion can be written as mx double dot minus 0 plus kx equals to 0, or mx double dot plus kx equals to 0. So this is the equation of motion generated by using Lagrange equation. I think it's pretty easy, isn't it? Because you don't need to draw the free body diagram. Alright, next we're going to look at another example here, which is 2 degree of freedom, still a translational vibration, whereby I have mass 1, 2 masses here, m1 and m2, and we have a spring here, k, and then we have 2 direction, which is moving to the right. So the first step, what I always do is that I always write the generalized coordinate. I always list it. So we know that it's a translational vibration, therefore the generalized coordinate will be x1 and x2. Okay, we have 2 here, which is x1 and x2. And then the total potential energy, sorry, I will start with total kinetic energy. Total potential energy sorry, I just need to double check something. Total kinetic energy T is equals to, because we've got two mass here, we've got m1 and m2, therefore the total kinetic energy would be m1 x dot 1 squared plus half m2 x dot 2 squared. Okay, it's different with the previous total kinetic energy equation, because in here we've got two mass, therefore it is half m1 x1 dot squared plus half m2 x dot 2 squared. And the next is the total potential energy. V. Okay, we know that V is half k delta x squared, because it's a delta here. Okay, and in here we looked at the k here, the spring here is attached or will react with x1 and x2. So delta x would be x2 minus x1, because it's a difference between x2 and x1. Therefore, the total potential energy would be half k x2 minus x1 squared. Alright, so we're going to use Lagrange here. I write the equation again, in order for you to see it clearly. D over dt, dt over dq dot j minus dt over dqj plus dv over dqj equals to q capital J. So because in here we've got two generalized coordinate, which is x1 and x2. So let's start with x1 first. So for q, maybe I use the next page. So for q equals to x1 d over dt dt over dq dot j maybe I write one by one first. dt over dq dot j is actually dt over dx dot, which is dt over dx dot 1. So if we differentiate t over x dot, we will get m1 x dot 1. So d over dt dt over dx dot 1 is equals to m1 x double dot 1. Okay, if you differentiate this one towards time, we will get m1 x double dot 1, and dt over dx is equals to 0. y0 because in here we don't have any terms of x, we only have terms of x dot. So dt over dx1 is 0. Moving on. So dv, now we move to the potential energy. dv over dx1. So we differentiate v, okay, towards x1. Okay, what we will get is that we will get k x2 minus x1 and then don't forget to differentiate the inner part, which is x1. It will be -1. Okay, this is on the maths, yeah. So we will get minus k x2 minus x1, and I normally always inform all of my students to sort of like arrange everything, which whereby we can also write it as k x1 minus k x2. Okay, rearrange back because we're going to put it in the matrix form, so we arrange it x1 first and then x2. Okay, so for the force q1 is equals to 0 because in here there's no external force, it's a free vibration, therefore it's 0. Therefore, using Lagrange, we can write the equation for x1 as m1 x double dot 1 minus 0 plus kx1 minus kx2 equals to 0. m1 x double dot 1 plus kx1 minus kx2 equals to 0. Okay, that is for x1. So going to proceed with x2. So for q is equals to x2 dt over dx dot 2 is equals to m2 x dot 2, and if I differentiate this against time, so I will get m2 x double dot 2, and then for dt over dx it will become 0 because we don't have any terms of x dot x. So for the potential energy, dv over dx2 is, so now we're going to differentiate this one towards x2. So we will get k x2 minus x1. Don't forget the inner part, which is x2. If you differentiate x2 towards x2, it will become 1. Therefore, it is k x2 minus x1. Then we arrange back, we will get negative kx1 plus kx2. Alright, for the force, q2 is equals to 0 because we know it's a free vibration. Therefore, the equation of motion would be m2 x double dot 2 minus 0 minus k x1 plus kx2 equals to 0, or we can write it as m2 x double dot 2 minus kx1 plus kx2 equals to 0. So this is for q is equals to x2, and this is for q equals x1. So if we combine both of that term in the matrix form, you can write it as m1 0 0 and 2 x double dot 1 x double dot 2 plus kx1 minus kx2, so kx1 minus kx2 minus kx1 plus kx2 x1 x2 equals to 0. So this is the equation of motion construct by using Lagrange equation. Alright, so we have looked at two examples of translational vibration. How about torsional vibration? I'm going to show you how we're going to do it. So it's actually the same. Alright, it's just the term of the Q here. Alright, start with Q. So the generalized coordinate here, because it's a torsional vibration, we know that the Q is theta because it's a torsional vibration. And in here, because we've got three second mass moment of inertia, which is J1, J2, and J3. Therefore, Q is equal to theta 1, we've got theta 2, and also we've got theta 3. And for the potential energy, total potential energy, T is half J1 theta dot 1 squared plus half J2 theta dot 2 squared plus half J3 theta dot 3 squared. So this is the potential energy. Sorry. So because we've got three second mass moment of inertia, J1, J2, and J3, therefore we have three terms here for J1, J2, and J3. Moving on, V, you know that V is actually half K delta theta squared, because we've got, so the first one for K T1 here, the KT1 will react with theta 1, so it will be half KT1 theta 1 squared. And then the second one, which is KT2, okay, half KT2. You know that KT2 reacts with theta 1 and also theta 2, okay, to cause reaction. Therefore, because it's a delta, so theta 2 minus theta 1 squared. And third one, we've got KT3. KT3 will react with theta 2 and also theta 3, therefore half KT3 theta 3 minus theta 2 squared. Alright, so using Lagrange, we know that Lagrange is d over dt, dt over dq dot j minus dt over dqj plus dv over dqj equals to q. So for q equals to theta 1, okay, so dt over d theta dot 1 is equals to j1 theta dot 1, and d over dt over d theta dot 1 is j1 theta double dot 1, and dt over d theta is equals to 0. Okay, so we have done this. Now we're going to look at dv here. So dv over d theta 1, so we're going to differentiate v over theta 1. We're going to differentiate this towards theta 1. What we will get is that in here we have two terms of theta 1, one in here and then another one in here. So when we differentiate towards theta 1, we will get kt theta 1 plus this is kt1, kt2 theta 2 minus theta 1, and then don't forget the inner part, which is this 1, differentiate this, minus 1. So we get kt1 theta 1 minus kt2 theta 2 minus theta 1. Okay, and then we can also write it as kt1 theta 1 plus kt2 theta 1 minus kt2 theta 2, and we factorize this, we will get kt1 plus kt2 theta 1 minus kt2 theta 2. So for the force, we know that, okay, so if we look here at the problem, you can see that there are three external moments, which is mt1 and mt2 and mt3. Okay, this is not a free vibration, this is a forced vibration. Therefore, q1 is actually mt1. Therefore, by using Lagrange, so j1 theta double dot 1 minus 0, maybe you don't need to do that minus 0 straight away, plus kt1 plus kt2 theta 1 minus kt2 theta 2 equals to mt1. Alright, this is for q equal to theta 1. So we've got the remaining two more. So for q equal to theta 2, okay, I straight away do this, d theta dot 2 is equals to j2 theta dot, and for d over dt dt over d theta dot 2 is equals to j2 theta double dot 2, and dt over d theta dot, theta 2 is equals to 0. For dv over d theta 2, so let's look in here. We've got two terms of theta 2 which is in here and also in here. So if we differentiate this towards theta 2, we will get kt2 theta 2 minus theta 1. Okay, multiply by 1, don't forget this one, plus kt3 theta 3 minus theta 2. Okay, don't forget this one, multiply by minus 1. So kt2 theta 2 minus kt2 theta 1 minus kt3 theta 3 plus kt3 theta 2. If I rearrange everything, we will get minus kt2 theta 1 plus kt2 theta 2 plus kt3 theta 3, theta 2. If you rearrange everything, minus kt3 theta 3. Alright, next, q2 is mt2. Okay, since the general coordinate is theta 2, therefore q2 is mt2. Thus the equation of motion would become j2 theta double dot 2 minus kt2 theta 1 plus kt2 plus kt3 theta 2 minus kt3 theta 3 equals to mt2. Alright, so for the last one, for q equals to theta 3, you know that dt over d theta dot 3 is equals to j3 theta dot 3, d over dt, if you differentiate it against time, dt over d theta dot 3 equals to j3 theta double dot 3, and for dt over d theta 3, 0, because you know there is no term of theta 3. So for dv over d theta 3, so we're going to look back here. So for theta 3, we only, because we need to differentiate v towards theta 3, we only have one terms of theta 3 here. Therefore, dv over d delta 3 would become kt3 theta 3 minus theta 2. Alright, don't forget the inner part here. divided by 1. Or I can write it as kt3 theta 3 minus kt3 theta 2. Don't forget to rearrange. Minus kt3 theta 2 plus kt3 theta 3. So for q3 is equals to mt3. Thus, the equation of motion for q equal to theta 3 would be j3 theta double dot 3 minus kt3 theta 2 plus kt3 theta 3 equals to mt3. So we already have all of the equations for theta 1, theta 2, and theta 3. Okay, this is the second one. And this is the first one. So next, if we combine everything together in a matrix form, therefore the equation of motion would be J1 0 0 0 J2 0 0 0 J3. We've got theta double dot 1, theta double dot 2, theta double dot 3 plus, alright, so the first one is kt1 plus kt2 theta 1, kt1 plus kt2 theta 1. So for this one, and then second one is minus kt2 minus kt2, and the third one is 0 because you don't have any terms for theta 3. This one would be theta 1, theta 2, theta 3 equals to mt1. Maybe I should give some space here. Theta 1, theta 2, theta 3 equals to, the first one is mt1. Alright, next for the second one, for q equal to theta 2 minus kt2, for theta 2, for theta 3 minus kt2 minus kt2, and in here is kt2 plus kt3. Sorry, I forgot. kt2 plus kt3. kt2 plus kt3, and the third one is minus kt3. Minus kt3 and mt2. Right, so for theta 3, it'll be this one and this one. So this is 0 minus kt3 theta 2 plus kt3 theta 3 equals to mt3. So this is the equation of motion in matrix form. Construct by using Lagrange equation for 3 degree of freedom torsional vibration. Alright, so it's pretty easy basically using this Lagrange equation. So it's an alternative of using Newton's second law in order to construct the equation of motion. So that's all for this session. Hope to see you again next time. Thank you very much. Bye.